Continue with some examples using Taylor series. Write the Taylor series for 1 over 1 minus x centered around x equals 0. This was one of the 5 that you should be familiar with already. So if you recall, you get 1 plus x squared plus x cubed plus dot dot dot. With that in mind, I'd like you to write the Maclaurin series for 1 over 1 plus x squared. Now remember, a Maclaurin series is centered around 0. So it won't tell you you should be centered around 0. You should know that as soon as you see Maclaurin. So how do we deal with this? Do we go through the whole process of the Taylor formula, finding all the derivatives, plugging in the value of 0? No, we don't need to do that. Because we know 1 over 1 minus x, we can look at 1 over 1 plus x squared as 1 over 1 minus the quantity negative x squared, and we can simply replace negative x squared for all the x's in the 1 over 1 minus x Taylor series. And then we just need to simplify. And there you have it. Not much work at all. So 1 minus x squared plus x to the 4th minus x to the 6th, etc. How about writing the Taylor series for arctan centered at 0? Well, if you remember that the integral of 1 over 1 plus x squared equals arctan of x, then this should be easy to do, because I just showed you how to get 1 over 1 plus x squared, the Taylor series for that. So now I want to integrate the polynomial 1 minus x squared plus x to the 4th minus x to the 6th. And so just take each term and find its antiderivative, which is fairly easy. So we get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, etc. And there we have the Taylor series for arctan of x, centered around 0. Let's write the Maclaurin polynomial of degree 9 for x over x squared plus 1. And once again, if you don't see the connection with one of the Taylors that you are familiar with, you could always do it by hand the long way. Find f of 0, find f prime of 0, f double prime, triple prime. Keep going until you get the 9th derivative, and then plug it all into the Taylor formula. Or you could think of this rational function as x times 1 over 1 plus x squared, which we've already talked about, and we know what the Taylor for that is. And then we'll multiply that Taylor by x. Now this one only wants degree 9, so I'm going to take the 1 over 1 plus x squared out to the x to the 8th term. And then I'm going to be multiplying that by x, so I will get an x to the 9th for my highest power, and then I'll be done. So there we have the 9th degree Taylor polynomial for x over x squared plus 1, which is also the Maclaurin polynomial because it's centered at 0. All right, how about writing the 3rd degree Taylor polynomial centered at x equals 1 for f of x equals the square root of x? Now this one is not a derivation of one of the 5 that we're familiar with, so we're going to have to do this one from scratch. So we need to evaluate the function at 1, its derivative at 1, its 2nd derivative, and its 3rd derivative at 1. So this first step is finding all those derivatives and then plugging in 1 for x. With a little bit of work, we come up with all those values. Now we're ready to take those and plug those into Taylor's formula. So f of x, which equals the square root of x, is going to be approximated by the third degree Taylor polynomial centered around 1, and that's going to equal 1 plus x minus 1 over 2 minus x minus 1 squared over 8 plus x minus 1 cubed over 16. Let's take this one step further. Let's estimate the square root of 1.2 using this Taylor polynomial. When I plug it in on my calculator, because I didn't want to do this one by hand, I got the third degree Taylor evaluated at 1.2 gave me 1.0955. Then I wondered, what would the calculator give me for the square root of 1.2? And the error I got, the difference between the square root of 1.2 and my Taylor evaluated at 1.2, the error wound up being 5.488 times 10 to the negative fifth power, which is a pretty small error, depending on your view of it. So that leads me to ask, well, is there any way we can estimate what the error will be in general? And obviously Taylor already thought about that. And so Taylor came up with a theorem that says if f has derivatives of all orders on an interval containing c, that's where we're centering it, then for each positive integer n and each x in that interval, there exists some number, we'll call it z, that's between x and c, such that the function f of x, which is the one we're approximating with our Taylor polynomial, if we go and take our Taylor up to the nth degree, then the amount of error that we're going to be off by is going to be this last term in blue, which almost looks like the n plus first degree term in your Taylor polynomial, but not quite, because we have a z there instead of c. So what it's saying is the amount of error is going to be, well, the first term that you leave off, except we're not going to evaluate the n plus first derivative at c like we do for all the other terms. We're going to evaluate the n plus first derivative at some number that's between c and our particular x value that we're approximating our function at. For example, when we were doing the square root of x, and we did that one at, what did we do that, 1.2? That's the x value. We'll go back to that for a second. We were approximating the square root of x at x equals 1.2, and this one was centered around x equals 1. So this z value that we're talking about, in this case, is going to be some value that we'll pick between 1 and 1.2 that'll make that first term that we left off as great as possible. And that last term is called the Lagrange form of the remainder. So as I said earlier, an nth degree Taylor only approximates a function, but by adding on this last term, which looks a lot like the first term left off in a Taylor series, that this will actually equal the function, and so this is actually going to tell us what the maximum error could be between an nth degree Taylor approximation and our actual function f of x. So let me try and spell this out a little differently, and then with an example, hopefully it'll be clear to you. So if a function f of x is approximated by an nth degree Taylor, given by our Taylor formula, if that's used to approximate our function f at a particular value of x, like we did at x equals 1.2 in that other example, then the error between the actual value of the function and the approximated value is going to be less than or equal to the absolute value of, as I had on the other page, what looks like the n plus first term in the Taylor polynomial, except the n plus first derivative is evaluated at some number z, which is between x and between where we're centered, our Taylor polynomial is centered at. And that z value we want to pick to make it as large as possible. So that will guarantee that our error will be less than or equal to that. So let's jump to an example. Find the error bound for the fifth degree Taylor polynomial centered at the origin for the sine of 0.2. So we're trying to come up with the fifth degree Taylor for sine, and then we want to approximate the sine of 0.2 using that Taylor polynomial and plugging in 0.2 for x. We want to know what's the maximum error, what's the error bound for that approximation. So hopefully by now we remembered the Taylor for sine. It's x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, etc. And we want the fifth degree, so we're stopping at the x to the fifth term. So the n plus first derivative, which would be the sixth derivative in this case, evaluated at some z, which we're going to figure out in a minute, over 6 factorial times x to the sixth. So according to Taylor's theorem, our error should be less than or equal to the absolute value of that. Now the sixth derivative of the sine function, you can work through it. First derivative is cosine, second derivative is negative sine, third derivative is negative cosine, fourth derivative is sine, fifth derivative is cosine, and the sixth derivative would be negative sine. But we're doing the absolute value here, so I just put positive sine. So this is the sixth derivative evaluated at z. We still have to come up with that z number, over 6 factorial times 0.2 to the sixth. The 0.2 is the x value that we're using to estimate our sine function. That comes from right here. Okay, so now what is this z number? So z needs to be between where we're centered at, which is 0, and where we're approximating our function at, which is x equals 0.2. So we want to pick a number between 0 and 0.2 for z that'll make this as large as possible. So that would mean that we want the sine of z to be as large as possible to make that fraction as large as possible. And we know that the sine of z will be greatest at a value from 0 to 0.2 if we go to the right endpoint. The sine of 0.2 is greater than any other value between 0 and 0.2. So that's the number I'm going to pick for z, because that'll make this as big as possible. And so we get that our error for using a fifth degree Taylor to approximate the sine of 0.2, our error is going to be less than or equal to 1.77 times 10 to the 8th, which is a pretty small number. So that means even only doing a fifth degree Taylor for sine, we're getting a really good approximation for the actual value of the sine of 0.2.